And again, we're talking theory here. So we want area under a curve, right? Yesterday, the day before, we were working with subintervals that are the same size. Piece of cake. Today, we need to address, and we need to, in math, you have to address every single possible issue. It's called generalization. This is how you generalize integrals. Okay? The man named Riemann that taught us stuff, he was smart. But you can see the nested arrays of subintervals that are different sizes. Right? This would be a left-handed Riemann sum, but these are all different sizes, which we don't know how to work with in our present structure of yesterday. So, what we have to do is kind of set this up. And each one of these is going to have a unique width, right? So we're just going to call each width change in x sub I. So this would be width 1, and then this next one would be width 2, then width 3. Okay, but the I is just a variable that can change. So you can see how we can build a sum out of that, right? Sure. And then the height of the rectangle, we're going to call these x values c sub I. So c1, c2, c3, right? So the y values are going to be f of c sub I. And now we can write a sum from I equals 1, right? You want width 1, x value 1, y value 1, those all pair up together. And again, number of subintervals. Height of the rectangle, width of the rectangle. But it's just a lot of encoding. Like instead of simply writing it, right? You just have to find a way to encode this so that each rectangle width is considered different. That's what we have to do here. That's why, so before we had to change an x, no I, because they're all the same, right? So now we have to consider each individual one.
So each individual one?
No, this is how we generalize it. We're not going to have to calculate this whole thing, right? Because you have the power rule, you have substitution, you have trade-off, you have all your tools. This is just the theory behind it. Okay? If you're in calculus in college, you might see this. If you're a math major, you'll see this in what's called complex analysis. It's the theory of calculus. Or real analysis. Okay. I actually had to write proofs for this stuff. Yeah, it sucked. Because there were like 50 different symbols all over the place. And I keep track of it. But this is the sum of the area under that curve. So we define the area under that curve. Approximate, right? The question is, how to make that an exact answer? What would you take to infinity? Okay, so it's going to be a limit, obviously. We're working with limits, right? So the trick is this part right here. What if I made n go to infinity? Not necessarily. Sure, and still needs number of subintervals. Yeah, so it's the number of rectangles. Okay, so if I take the number of rectangles to infinity, am I changing their size at all? Not. See, with the other one, what we did was we took the number of rectangles within a certain area.
So that it is an interval,
What if I took, consider this, I equals 1 to infinity? 1 rectangle, 2 rectangles, how many rectangles am I going to have? An infinite amount, are they going to be small? Not necessarily. Right? So with the other theory, we made the rectangles really small, right? Is there a way to make these small?
Oh my gosh.
Any guesses?
Absolute value of the absolute value of
This is the, you guess, the double bars. Maximum partition size. So maximum rectangle width. So we're taking the max rectangle width to 0.
Is this one a calculus?
No. This is completely preparing for college. So, and I need to expose you to the theory and stuff. So you can see that we're taking this is my biggest rectangle, right? I'm trying to make it 0 width. Okay, so it's going to obviously increase the number of subintervals. Right? So we have the same situation as yesterday, we just have to state it differently because of a different situation. Yeah. So we're taking the sizes of these all to 0. And we're going to have an infinite number of rectangles that are 0 wide. And we have an integral. Okay. So this is actually the definition of an integral. So much prettier than this, right?
So much prettier, I love that so much.
Choice A or choice B? Yeah, I agree. This is where we get the theory that allows this to work.
I'm not doing it.
Okay, that's fine.
It's not it's
So, again, 2 different approaches. Yesterday, we took n to infinity because we had number of subintervals. That was really easy. Here we have to take the partition size 0 because we don't know how many subintervals there are because they're all different sizes. That's the key. We don't know that number. So we have to change this. This is pretty much saying the same thing. Height times width. Except right. So that's kind of the theory behind it. So, not going to ask you to do any calculations there, but we could. And it's not very difficult. You guys remember what sign there is and stuff, right? So if I draw this, it's all positive area, right? That's all negative. The total area would be positive, right? Yeah. Visually. So keep that in mind. Just you're subtracting out below the axis. Remember what absolute value does? somebody else. Right? I do this. Basically, it's the same one, but these are both going to be positive. Now it's going to do this. So that's what absolute value does. It changes everything goes positive. So absolute value is kind of nice to interrupt subtract area out, unless it's dropped below that size. Do I need to remind you what the power rule is? What is the integral of x squared? Yeah. Add 1 and divide by that number. The integral that rule, you might not be using it on the AP exam. You switch the integral limits, then you have to make it. It's not switch. It's switch.
Yeah, kind of wonder, like, that makes sense, just don't
Positive equals a negative, of course. These are very, very typical free response questions. You'll get that graph, and it'll say the starting value, let's say that here. The starting value here is 0. What is f at -5? If this is the derivative. And you have to integrate backwards, right? So make sure you're using that. If you're going backwards, it's a negative. Does that make sense? Okay, so if I were to say, if I were to say the total area here, and this is f prime, if the area is 5, what's the value of f at -5? Let's call it area 15. It's -15. Because you have to subtract that off, go backwards. It makes that negative. So if you backwards in the area under that, you positive? Basically, yeah, it's a good assumption. Let's see. Remember, you can split integrals up. You can split them up. This would be the associative problem. You can use that to your advantage. A lot of times if you're calculating area between two curves, you need to use that because they flip flop. Top minus bottom is negative, and you have to flip them.
Yeah.
Top minus bottom is negative. That's where you'll use this supposed to be. That ring about?
Yeah, and then solid evolution with it.
So that would be like, if it went positive, negative, and
That one looks really cool and solid.
like, let's say if it was
That's automatically gonna work.
oh,
So the sine function is probably the best example of that.
we're like in it would be like
What's the area? 0. If you take the integral, it's cosine cosine 2 pi minus cosine 0, you get 1 minus 1, 0. It automatically works. Where it doesn't automatically work when you have dual curves and stuff. Yeah, so that's automatically going to work. You do not have to split that up. And so, just a reminder. Whoa, hold on. I'm still in derivative mode. Integral from 0 to 2 pi of sine x. Negative cosine? Yeah. Negative cosine x value from 0 to 2 pi. So the negative cosine 2 pi minus negative cosine of 0. Which ends up 0. Okay. So evaluating the integrals. Remember on indefinite integrals, you gotta put plus c. I don't think they're running that here. Is that enough? Kind of jogs your memory on integrals. Okay. Square,
That makes sense until you start rotating it and that
it's actually next chapter.
That's if you have
It's been washed in there.
That's when you have to
Isn't this high?
I got 40 million dollars.
I just want to get it. Okay, there you go. See you tomorrow.
Wait, did you already do the APs already? Well, I mean, did you already sign this?
No. You guys had APs to do yesterday. Yeah, she did great. Love that one so much. Didn't want the answers? Or you're just so good that you think they're all right.